Go ahead.
So it's with pleasure that I introduce Xianglong from Notre Dame. He's going to talk about great three perfect ideas and length four self-dual resolutions. Thank you, Shalom.
Thank you, thank you. It's a pleasure to be speaking at the seminar again. So what I'm going to be telling you about is ongoing joint work with Timik, Lorenzo, and Jerzy. And actually, I'll tell you the main goal that I'll try to get to at the end of this talk, which is actually not mentioned in the title, but it's the primary application of the apparatus that I'm going to show, which is to give a structure theorem for grade 4 Gorenstein ideals generated by at most 8 elements. Now, what I like to start off with is to explain what I mean by structure theorem, and also to explain a little bit this somewhat unfortunate restriction that's only up to 8 elements. So first, let me talk about what I mean by structure theorem. I think the best way to explain is by example. In particular, I'll talk about perhaps the most classical structure theorem in this regard, which goes back to Hilbert in 1890, and later generalized by Birch in 68. So the Hilbert-Birch theorem says that it gives a structure theorem for cyclic modules R mod I of projective dimension 2. And so it says that if a complex of the form Rn n minus 1 to R to the n to R is a cyclic, let's call this D2 and D1, then in fact D1 is some non-zero divisor times the maximal minors of D2, which I'll write as wedge n minus 1 of D2 dual. And so if you identify Rn with the dual of its submaximal exterior power, this is what you get. And furthermore, in fact, this is the best that you can do for resolutions of this type, because the generic example, if you take D2 to be a generic matrix, and then you take another indeterminate for this non-zero divisor, then the generic example is itself acyclic. So this is in some sense a universal resolution of the format 1 and n minus 1. Now, as a consequence, an immediate corollary of this, one gets a structure theorem for grade 2 perfect ideals. So let me first recall what it means for an ideal to be perfect. So let's say R is local. Let me say that I in R is perfect if the grade of I is equal to the projective dimension of R mod I, or in the language of free resolutions, I take a minimal free resolution of R mod I and look at its dual, and the dual is also acyclic, and it resolves the canonical module. The main case of interest in a lot of situations is if R is a regular local ring, then the condition that I is perfect is equivalent to the condition that the quotient R mod I is Cohen-Macaulay. And this just follows from the Alexander-Buchsbaum formula. Now, as a corollary of Hilbert-Birch, what we see is that if I is a grade 2 perfect ideal, well, then this non-zero divisor had better be a unit, which means that this is just then I is generated the maximal minors of an n by n minus 1 matrix. And again, this is the best that you can do because the generic example, where you take a generic n by n minus 1 matrix and then its maximal minors, is an example of a grade 2 perfect ideal. Right. Okay, so the next thing I want to mention is a generalization of the Hilbert-Birch theorem, and this is the first structure theorem of Buchsbaum and Eisenbud. So, Buchsbaum, Eisenbud, and this is in 1974. So this is a structure theorem for finite free resolutions. So the finiteness is very important here because it starts by working at the left end. Let's say I have a finite free resolution like this, say resolving M. Let's call these differentials di. And so for some more notation, let's write fi for the rank of the free module fi, and I'll refer to the sequence of numbers fi as the format of the resolution, and then I'll let Ri denote the rank of the differential di. So in particular, we have that Ri plus Ri plus 1 is equal to Fi. So, what is the first structure theorem of Buxbaum and Eisenbud? The structure theorem asserts the existence of unique maps AI, which are maps from R to wedge R I F I minus 1, and they are defined as follows. So, they're defined by downwards induction. So first we have that AC is just defined to be the top exterior power of the last differential. So this is wedge RC DC. And then, moving downwards on the index, what we have is the following. For every differential DI, so DI is a map from FI to FI minus 1, I look at wedge RI of this. Now notice that the previous, so I'm going to define what AI is, so I'm assuming that AI plus 1 has already been defined, and AI plus 1 should be a map from R to, so an element, in other words, of wedge Ri plus 1 of Fi. Now, since Ri plus 1 is just Fi, if I consider the map which is just wedging with AI plus 1, viewed as an element of wedge Ri plus 1 of Fi, and this will go to wedge Fi of Fi, which we identify, we fix the identification with R. And the first structure theorem of Buxbaum and Eisenbud asserts that you always have factorizations like this, so to define the next AI. Now, the main reason I want to mention this structure theorem is because I want to sort of say an informal remark, which is how one can think of these maps AI is that AI is effectively giving Plücker coordinates for the ith syzygy module. And I put this in quotes because, as written, this statement is not literally true, because I don't know what it means to talk about the Plücker coordinates for the syzygy module, but at least this is true on the nose, for instance, on the complement of sub M, because then it's just a split exact complex, and then the syzygy module is just a direct summand, and then this is true, like, with no fine print. This is just a true statement. Okay. So, the sense of the first structure theorem of Buxbaum and Eisenbud can actually be recast in also this language of like universal objects. So, I'm not really going to go into great detail on this. This is not sort of tangential to the main thing I want to talk about. But But I'll say a little bit about this, which is the question. This was posed by Hochster in 75, and also he addressed the case of length 2. Is do there exist universal free resolutions of any given format? Or maybe I should say any given plausible format. And this is actually a very rich story with a lot of literature about this, but I only actually want to talk about one particular result in this direction, which is Bruns in 84 showed that, in fact, these universal free resolutions don't exist, so you have to actually weaken the condition to genericity, which is to say that you don't require that the specialization from the generic guide to your particular guide be unique. Now, the reason I want to talk about Bruns's argument, which I'm going to paraphrase, I'm not going to say it exactly the way that he said it, is because it uses a trick that has been that's proven useful over and over and again in this project. It's a very nice trick. So here is Bruns's argument, paraphrased. So suppose that we have a universal pair is a universal free resolution for its given format. And Bruns's insight was that if it's a universal free resolution for its format, it actually turns out to already be universal for complexes that are acyclic in grade 1. And the way that he argued this is as follows: so suppose that RF is a complex with the same format that is a cyclic. Oops. is acyclic in grade 1. And when I say something is true in grade 1, I mean it's true localized on any prime of grade at most 1. Or it's more generally acyclic in grade C will mean that similar thing. So what Brens showed is that, well, in fact, there must already be a map from this universal ring R to R, specializing F universal to F. And the way he argued this is as follows. So again, paraphrasing a bit, let me write Z to be, say, the support of the positive homology of F. And then the assumption that this F is acyclic in grade 1 implies that grade Z is at least 2. Now let me define U to be the complement of Z, so spec R minus Z. So Brens's insight was that the uniqueness of the specialization from the universal ring would imply that working affine locally on U, well, since affine locally on U, your complex F is actually acyclic, that means that there must be a map from the universal ring to each of those rings. But the universality and the fact that the specialization is assumed to be unique means that you won't run into problems trying to glue this. So you can define this map from U to spec of R universal affine locally. So can glue because specialization can, I say, work affine locally and glue because specialization from universal ring is unique. Okay, but then the next observation was that if you've defined it from U, then actually it extends to spec R. And this is because the complement of U is grade, well, at least 2. And here I'm using the fact that, well, what is this picture? Really, I have R universal, I do the sections on U, but then I have a restriction map from global sections to the sections on U, but this is an isomorphism. So this is a restriction, it's an isomorphism, because grade Z is at least 2. Okay, so that means I actually get a map from the universal ring to R, specializing the universal resolution F to F. And all that I didn't assume that F was acyclic, I only assumed that it was acyclic in grade 1. But what this shows is that at best you can hope for a universal example of a complex that is acyclic in grade 1 instead of one that is acyclic everywhere. And in fact, the first structure theorem of Buxom and Eisenbud already does that. So in some sense, the first structure theorem of Buxom and Eisenbud is the best thing you can hope for if you insist on unique specialization from the universal object. But the main reason I want to talk about this was mostly just to highlight this trick of essentially what one might call heart hogs, right? The idea that if you're able to define it on the complement of something of grade at least 2, that extends to all of R. So the next thing I want to talk about is another structure theorem, which will be somehow the prototype that we want to generalize to grade 4, which is another structure theorem of Buxom and Eisenbud, but this is from a different paper. And what this is for grade 3 Gorenstein ideals. So let I, grade 3, Gorenstein ideal. And in this talk, when I say Gorenstein, I just mean that it's perfect and the last Betti number is 1. So in the usual setting, for instance, the ambient ring is a regular local ring, this just reduces the usual definition that R mod I is a Gorenstein ring. So R mod I, the claim then is that mod I has a resolution of the form like this, where D2 is a skew matrix and D1 consists of some maximal Thaphians of D2, and here n is odd. And once again, like the case of the statement earlier from Hilbert Birch for grade 2 perfect ideals, this is the best that you can do because they also show that the generic example, that if you take D2 to be a generic skew matrix, then that is also an example of a grade 3 Gorenstein ideal. So in that sense, this is the best structure theorem you can hope for this class of ideals. So I want to just say briefly about the main ingredient that goes into this proof, because we're going to use this ingredient later as well. So the proof uses a choice of multiplicative structure on the free resolution F. So indeed, in this same paper, they established that you take a resolution of a cyclic module, they'll have the structure of a graded commutative differential graded algebra, which need not be strictly associative, but in the case that your resolution has length 3, there's basically not enough space for associativity to fail, so it ends up actually being strictly associative. Then they use this multiplicative structure to take the resolution and put it in this form that's stated in the theorem. Okay. So actually, a few years prior, independently, right, so although n being odd was part of this theorem, this had already been proven a few years prior by Watanabe. So in fact, his proof showed something else as well, which is that if I is a grade 3 Gorenstein ideal, then I is Lichy, which is to say I is in the linkage class of a complete intersection. Now, I'm not going to talk a whole lot about linkage in this talk, so I'm not going to really go and define this. For the time being, you can just think of Lichy as being an adjective that just means nice. And to give you an idea of what nice entails, so Buchweitz and Herzog, so Herzog in 80 and Buchweitz in 81. So again, I'm going to be very hand-wavy about this and just say Lichy ideals have nice deformation theory. And if one makes this more precise, the idea is that somehow, in retrospect, the explanation for why there could be such a nice structure theorem for grade 3 Gorenstein ideals is intimately related to the fact that all such ideals are Lichy. And okay, so now that I've gone this far, I want to go back to the original goal that I stated I was going to try and do this talk, which was to get a structure theorem for grade 4 Gorenstein ideals generated by MO state elements. So now that I've stated Buchsbaum-Eisenbud, that's sort of what I have in mind for as far as structure theorem goes. So the other thing I wanted to explain is why is there this at most 8 elements condition, and that's related to what I was just saying a moment ago, which is that it turns out for grade 4, the analog of Watanabe's result is not true. So there exist grade 4 Gorenstein ideals generated by 9 elements that are not Lichy. So this suggests that in grade 4, the study is somehow it can be much more complicated in this situation for grade 3 Gorenstein ideals. Okay, so taking a step back and looking at what's there, right? So we have a very nice structure theorem for grade 2 perfect ideals coming from Probert Birch. We have a very nice structure theorem for grade 3 Gorenstein ideals coming from Buchsbaum-Eisenbud. And grade 3 Gorenstein means grade 3 type 1, right? Cohen-Macaulay type 1. So given that grade 3 type 1 is settled, where the next two, I guess, easiest cases that one might consider, well, one might increase one of the two parameters by 1, right? So for instance, we might say, let's stay in grade 3, but look at type 2. Or one might say, let's keep the type 1s, we're still looking at Gorenstein ideals, and look at grade 4. So the two next natural cases to consider, right, so grade 3 perfect type 2 or grade 4 Gorenstein. So let me just say a few words about the work that's been done in each of these two cases. So for the case of grade 3 perfect type 2, and Brown gave a structure theorem for some of these ideals with the assumption that they were essentially directly linked to an almost complete intersection, which is some condition on there being minimal causal relations in the minimal free resolution. That being said, this is not exhaustive, and even in the sort of smallest new case, which is, say, perfect ideals with Betty numbers 1, 5, 6, 2, the family that Brown described was not the only family, and this was demonstrated already in her paper. She gave an example of an ideal that did not belong to that family, but then much more recently, Silikbas, Laxmi, Kraskevich, and Weyman gave essentially the generic example of this other family of perfect ideals with Betty numbers 1, 5, 6, 2. And then this was later also studied more by Custon, who gave a more characteristic free description of this family. So actually, on this left side of a grade 3 perfect I2, there's other work done in like the grade 3 setting, but mostly it's always been done using the tool of linkage. Now, on the other side, whoops, I did not mean to erase that. I would say there's been comparatively more literature, so I'll at least just say a few things. So for instance, the first non-trivial case, so maybe I'll first say it right. So if you have a grade 4 Gorenstein ideal, so it's just generally known that if you have a grade C Gorenstein ideal, it can't be minimally generated by C plus 1 elements. This is a result of Kunz. So the first interesting case will be the case of C plus 2, so 6 generated grade 4 Gorenstein ideal, and Herzog and Miller in 85, and later the hypotheses were weakened a bit by Vasconcelos and Villarreal in 86, showed that if you have a grade 4 Gorenstein ideal generated by 6 elements, then actually it's just a hypersurface section of a Buxom-Eisenbud example, so a 1551 ideal. But there are lots of examples of grade 4 Gorenstein ideals that are not hypersurface sections. So actually a few years prior, maybe I should have mentioned this first, right, so Custon and Miller in 82 gave examples of grade 4 Gorenstein ideals that are generated by any odd number of elements. So in particular, being generated by an odd number of elements, they can't be a hypersurface section of a grade 3 Gorenstein ideal, because those were already generated by an odd number of elements, so a hypersurface section of them must have been generated by an even number of elements. And I'll also mention Mausried, who has written many papers on this topic, but in particular a lot of them with co-authors focusing on the case of these 9 generator ideals that they've called Tom and Jerry, for instance, which are related to like the 2x2 minors of a 3x3 matrix, or the 2x2 minors with 2x2x2 tensor, for instance. So there's lots and lots of work on the grade 4 Gorenstein case. I'd say more than, say, on the left side compared to this grade 3 perfect type 2 case, but somehow the punchline of the first half of today's talk is going to be that these two seemingly very different families of ideals are actually very, very closely related. And the sense in which they're very closely related is I'll show you a construction that goes from one to the other and back. Okay, but before I do that, are there any questions? Maybe I'll pause here for a moment. Okay. So the first construction, so I guess all the preceding was background, so now it'll be section 2, the constructions. So the first one is relatively easy to say, so I'll call this theorem 1. So we start with a resolution of a grade 3 perfect ideal. So let A3, A2, A1 to R, let's say this resolve R mod I, where I is grade 3 perfect. So now I'm going to fix the multiplication on A, which I'll just denote by dot. And the decomposition of A3 as C plus L, where L is just R1, and these are both free. Then from this data, I'm going to construct a new complex that I'll call B. So define B as follows. So the last differential here will be from C to A2, and this is really just all but one column of the original D3, so I'll call these D, D2, D1. So I'm taking all but one column of D3 as my last differential of B, and then next I'll have a map from A2 to A1, which is just D2, but I'll also have a map from A2 to A1 dual tensor L, and I'll define this in a moment. Then the rest of this whole picture is going to be dual to the left side. So this will be D2 dual, mapping to A1 dual tensor L. This map will be dual to this other map that I haven't defined yet, and this one will be dual to D3. So this will go to C dual tensor L. So what is this map? So where A2, A1 dual tensor L, explicitly is given as follows. If G is an element of A2, I send it to the following. So viewing A1 dual tensor L as linear maps from A1 to L, I'll define it to be the map that sends an element of A1 to what happens if I multiply it with G. This gives me an element of A3, and then I project it onto L. Or another way of saying this is i.e. it's adjoint to the multiplication A1 tensor A2 to A3 projected onto L. Right, so I define a map from A1 tensor A2 to L in that way, and then I just move the A1 factor to the other side, and I get this map. Right, so that's the definition of B, and the claim of the theorem, then, is the following, is that if, so let me say this last over here, I'll use deltas to denote the differentials of B. So if the ideal of maximal minors of delta 4, which is to say the sum matrix of D3 that consists of all but one column, if the grade of this ideal is at least 4, then B is acyclic. So it turns out, oh, by the way, yeah, so if it happens then that B is acyclic, then it follows that the ideal, this ideal here has grade exactly 4, right, because the ideals of all the minors in this resolution must have grade 4. So in particular, and the proof turns out to be surprisingly very easy, and the idea is the following. So using either the Peskin-Spiro acyclicity lemma or the Brooks-Eisenbot acyclicity criterion, so I tend to think of things using the latter. It suffices to prove that if you want, right, so if you want to show that this is acyclic, it suffices to prove that the grades of the ideals of minors of differentials are at least 1, 2, 3, and 4, respectively. Now, a posteriori, if we know that this thing is acyclic, actually all the grades are equal to 4, but I don't need to prove that, right? I don't need to actually show that to prove that B is acyclic. But in particular, since I'm assuming this guy already has grade 4, it would suffice to show that the grades of minors are 1, 2, 3, 3, which means it will be enough to prove that this complex B is acyclic in grade 2. And so it suffices to prove, not sure why my pencil is acting up like this, suffices to prove that B is acyclic in grade 2. And again, what I mean by being acyclic grade 2 means it's acyclic when localized in a prime of grade at most 2. But then the next observation is that this construction of B from A, all it uses is just the differentials of A and the choice of multiplicative structure, but in particular is compatible with localization, right? Because I can also just localize the multiplicative structure to get a multiplicative structure on the localization of A. So what this means is I reduce at once to, well, if I localize A at a prime of grade at most 2, then it just becomes split exact, right? Because this is a resolution of a grade 3 perfect ideal. So we reduce, so since the construction of B is compatible with localization, reduce to the case that A is split exact. And And then it just becomes actually a straightforward computation. You can just write, you can explicitly parameterize all possible parameterization, or all possible multiplications, rather, of on a split exact complex A, and then just show that regardless of what multiplication you choose, the complex B you write down will just be evidently split exact. You just write down very explicitly differentials. So I'm not going to do it here, but I should comment that everything I'm talking about right now is available. This stuff has been posted on the archive actually very recently, just like a day or two ago, so you can find the details all worked out there. Right. So now I want to comment a bit about potential generalizations of this. So I'll mention that independently, Pollini and Ulrich in unpublished work have shown that if I is a... Well, I should also say that the main case of interest, right, the main case of interest is when A3 is R2. So the starting ideal is a grade 3 perfect ideal of type 2. In that case, then the output, right, then the C is also R1. So then the output is a resolution of a Gorenstein ideal of grade 4. Right. So, output of Gorenstein ideal of grade 4. Right. So Pollini and Ulrich have shown that if this actually holds in some sense in more general, in greater generality, at least for the case of type 2, so which is that if I is a grade C type 2 perfect ideal, and J is generated by a column of the last differential in a resolution of I, then if grade J is C plus 1, then it is Gorenstein. And they use a theory of residual intersections to prove this. So then a follow-up question is, to what extent is this construction reversible, right? So like, do you get all grade C plus 1 Gorenstein ideals in this manner? So I'll point out right now that if you take C to be 2, then the answer is certainly no, because, well, let's say you start with a grade 2 perfect ideal of type 2, then the embedded numbers of R mod I must be 1, 3, 2, right? It has to be a resolution of the form R2 to R3 to R. But then in that case, you see just immediately that a column of the last differential is at most generated by 3 elements, right? So if it has grade 3, then it's going to be a complete intersection. So indeed, it is Gorenstein, but you're only getting complete intersections in that case. You're certainly not going to get all Gorenstein ideals of grade 3 by this construction. Now, the second main theorem that I'm going to talk about is actually that for C equals 3, this is reversible with some mild additional hypotheses that I want to explain now. So this is the reverse construction. But for the reverse construction, I have to impose some more hypotheses. So now for the remainder of section 2, assume that R is a unique factorization domain and contains 1/2. Okay, so the reason for these hypotheses will be made apparent shortly. So I'm going to start this time with a resolution that is explicitly self-dual. So in other words, a resolution of the form B0 dual to B1 dual to H plus H dual, which is B2 to B1 to B0. So I'm going to call the differentials of this guy deltas. So delta 1, delta 2, delta 3 will be delta 2 dual, and delta 4 will be delta 1 dual. Right. So I want to emphasize that I am assuming that this complex is explicitly self-dual, not just abstractly self-dual. As that's a rather strong assumption. In particular, it's not clear whether any Gorenstein ideal actually emits a explicitly self-dual resolution. This is, however, at least known under the condition that, say, the ambient ring is a complete regular local ring. So I'll mention this now. So Custon-Miller, AD. So if R is a complete regular local ring, and J and R is grade 4 Gorenstein, then R mod J has a resolution of the form B. And to comment a little bit more on this, so what they show is that as long as they already assume that throughout that 1/2 is contained in R, but then they show that if you have a grade 4 Gorenstein ideal, then R mod J has a resolution where the middle module with a symmetric isomorphism with its dual. But to furthermore put it in this like sort of split form, they have to assume that R is complete. Okay, so now I want to call back to the first structure theorem of Buxbaum and Eisenbud. So I mentioned back then that the first structure theorem, the maps you get, like these AIs, you should think of them as giving Kluger coordinates of, like, say, the images of the differentials in your resolution. But in this case, so, okay, I'm assuming that B is like cyclic. So what I claim is that in this particular case, the image of delta 3 is actually a very special type of summodule of the middle guy. It's a totally isotropic summodule. So let Q be the evident quadratic form on H plus H dual, just given by the pairing of the two factors. So let's see what happens if I take, like, say, V is an element of B1 dual, and then I take delta 3, I apply it to V, and then I evaluate Q on this. So let's say that this is a block matrix with X being the part that maps to H and Y being the part that maps to H dual. Then I can explicitly compute this. Well, this is just XV paired with YV. This is an element of H. This is an element of H dual. But then I can write this as follows. This is 1/2 Y dual XVV plus 1/2 X dual YVV. And this is 0 because, well, Y dual X plus X dual Y is none other than delta 2 delta 3, which is 0 because B is a complex. All right, so what this shows is that the image of delta 3 is totally isotropic summodule of B2. And throughout, whenever I say isotropic, I'll always mean totally isotropic. So the quadratic form vanishes identically on the summodule. Now, if I look, say, over the fraction field of R, then the image of delta 3 will define a legitimate point of the isotropic Grassmannian of isotropic M-planes in a 2-n-dimensional split quadratic space. So I'm going to make the following assumptions. I'll assume that over frac R, the image of delta 3 and H dual, so these are both rank n isotropic summands of this middle module. So I'm going to assume that they belong to different components of rank n isotropics in B2. Right, so the moduli of rank n isotropics actually has two connected components, and what I'm assuming here is that these two isotropics belong to separate components. They don't belong to the same component. And this is not a serious restriction. If this isn't true, then all you have to do is really exchange one basis element of H with its dual basis element from H dual, and then the condition will be met if it wasn't already met. So you shouldn't worry so much about this condition. It's just a technical condition. But what I'm going to do now is, so let Z be, say, the support of, well, I guess, yeah, the support of the homology of B, right, and then let U be the complement. So at least on U, the image of delta 3 is a legitimate isotropic summand of rank n. So what that means is that on U, I can define, I get a map, so let's put in quotes, define, this is determined by the image of delta 3 to the isotropic Grassmannian of n-planes in 2n-dimensional space, and this admits a Plucker embedding into the the projectization of a certain representation of the special orthogonal of the algebra, which is the half-spin representation, with the way, so it turns out that with this assumption that I put here, the correct half-spin representation is wedge odd of H. So what does this mean? So thinking about this composite, I get some projective coordinates, and so what I think of these as, I'm going to call these the spinor coordinates for the image of delta 3. At least these are defined over U. But the caveat is that since I have a map to projective space, these may only be valued in some line bundle on U. However, this is the reason I'm assuming R is factorial. So if I assume that R is factorial, then pick U is trivial. So I can just assume that these are actually valued in sections on U. So since R is factorial, get spinor coordinates valued in sections on U, but then I use this fact that, well, Z has a grade 4, so in particular has a grade at least 2, which means that these actually extend to R. Since grade Z is 4, which is at least 2, we know that R, the restriction is an isomorphism. In R. And I'm just going to denote this by A3 tilde. So this is a map from R to wedge odd H. And the reason I'm calling this A3 tilde is because it's related to the Buchsbaum-Eisenblatt multiplier A3. So going back to the earlier remark, right, the idea is that A3, without the tilde, is giving me Plüger coordinates on the image of delta 3 sort of in the ordinary Grassmannian. Right, so the isotropic Grassmannian certainly embeds into the ordinary Grassmannian of n-planes in two-dimensional space. And this has its like standard Plüger embedding into the projectorization of wedge n H plus H dual. Right? And then what's here is the degree 2 Veronese. Well, to be more precise, the degree 2 Veronese lands in the subspace of the lower guy. So here's what we have. So what this picture shows me is then that so this map is what corresponds to the Buchsbaum-Eisenblatt multipliers. So really what we see is that up to an overall unit, so I have a unit times sim2 of A3 twiddle is A3, the Buchsbaum-Eisenblatt multipliers. Or to put it in a different way, the spinor coordinates up to scale are square roots of certain Buchsbaum-Eisenblatt multipliers, and the prototypical example that you should keep in mind is, for example, if you have a skew matrix, right, then the various size Pfaffians of that skew matrix are square roots of certain minors of that square matrix. That's really what this is a generalization of. Okay, so I'm just going to do one more thing, and then we can take the break. So I'm going to define one last map, which is this. So I'll look at my complex here. 0, B1 dual, H plus H dual, B1. And I claim that if you take a map from, so if you take this other representation, wedge even of H dual, there's up to scale a unique SO equivariant map from this to wedge odd H dual tensor the standard representation. And then this maps to this via A3 dual tensor 1. And it turns out that what you get here is a cycle in this complex. So it lifts, not uniquely. And you choose a lift, and I'll call this W. Okay, so now with all this, I'm finally ready to state theorem 2, which will be the last thing I do before the break. So theorem 2 is intended to reverse theorem 1. So with all this machinery, I define the following complex A. A is the complex as follows. So from B0 dual plus R to B1 dual to H dual to R. And this map is just delta 3, or more precisely, it's delta 3 followed by the projection onto H dual. This map here has 2 parts. So all but one column, the part that coming from B0 dual is just delta 4, and this last column here so this map W is a map from wedge even H dual, but in particular wedge even includes wedge 0. So wedge 0 H dual is just R, so there's a map W restricted to I guess we'll wedge 0 H dual to be very explicit about it. So that's just a single column. And then this last map here, this is the restriction of the spinor coordinates A3 dual. I restrict it to H dual, because this was a map from wedge odd H dual. So in particular, in the bottom component, I just have H dual. So once I define this complex A, the claim is that if grade, let me call this guy D1, so I1 D1 is at least 3, then A is acyclic. But in particular, that means I1 D1 is a grade 3 perfect ideal. And the proof of this actually is more or less the same as the proof of theorem 1, which is, again, it suffices to prove this in grade 2, but then, well, not only in grade 2, but also under the assumption that if I localize at a prime of grade 2, then this becomes the unit ideal, right? This ideal becomes the unit ideal. So I can reduce to the case that the original complex B is split exact, and that this is the unit ideal. And then in that case, you can just spell things out explicitly and see that the complex you define this way is also split exact. Okay, so I think this may be a good time to pause for a break.
Yeah, it's a good time to stop. So is there any question for Xianglong?
Maybe I have one. Are you claiming in theorem 2 that this then recovers the original?
Right. So that's yeah. So this is a little bit. So I'm technically not claiming that. I guess what I am claiming, however, is that every if you have a explicitly self-dual resolution of length 4, then the last differential can be placed inside the last differential of a resolution of length 3 if you add one more column. In particular, the special case that we really care about is you have a grade 4 Gorenstein ideal, then there is a grade 3 perfect ideal that exhibits that grade 4 Gorenstein ideal in its last differential.
Yeah. Thank you.
So that does bring up a good question, though, which is like, to what extent are these two constructions like inverse to each other on the nose? And I suspect that like up to maybe potential rescaling of the differentials, if with an appropriate choice, there are some choices involved in the constructions, right? Like for the forward construction, for the first theorem, you had to choose a multiplicative structure, and likewise for this reverse theorem, you had to like choose a slift W. But I imagine that for like if you choose these compatibly, then you can really just recover the original things up like on the nose, or maybe up to scale by a unit or something.
So it's okay, Xianglong, if we start again at 625?
Sure, that works for me.
Okay. So you are just saying that really you can go backwards, at least if you're in a polynomial ring.
Mm-hmm. Yes. Oh, yes. So there is.
In the complete case, you can always go back. Everything works, so you can always go backward.
Right. So yeah, I guess I forgot to mention that case here. So indeed, so the Custon and Miller showed that if the ring is a complete regular local ring, then you can put your Gorenstein ideal in this explicitly self-dual form. But also, if you have like a polynomial, graded polynomial ring over a field, that this also works. Yeah. All right. So I just realized there were a few things that maybe I should comment on that I forgot to mention. So one thing is, so for more information about spinor coordinates...
Xianglong, maybe you shouldn't go so fast. You are going a little fast. Even for me, that I know the whole story.
Sure. Yeah, so let me... let me mention a few things. So let's say that this is a... If you want more information about spinor coordinates, then you can refer to the paper by Silikpas, Laxmi, and Weyman in 23. This is a construction of spinor structure on B in more detail. So I think what I want to do now is not entirely explicit example of theorem 2, but I'll demonstrate at least a sort of numerical example, as in I'll show you what happens to the graded Betti numbers in a particular example. And the reason I want to do this is because, time permitting, this might come back later at the end of the talk. So let me do an example of theorem 2. So let's say I start with a Gorenstein ideal, grade for Gorenstein, graded with Betti table 1, 16, 30, 16, 1, like this. So for example, e.g., J could be the 3x3 minors of a 4x4 generic matrix. Okay, so if you were to run this construction on this ideal, what kind of complex would you get in the end, right? Like, at least what kind of shifts would you see in the complex? So let's recall the definition of the various differentials in A. So the middle differential just comes from a piece of the middle differential of the original resolution. So that one's relatively easy to understand. But the first differential comes from the spinor coordinates, and we'll recall that these were square roots of certain Buxbaum-Eisenbud multiplier coordinates. So let's look at what that is. So if I take, so let's say B as res of J as the form B1, B0. So if I look at wedge 15 of B1 dual, wedge 15 of H plus H dual. Okay, so this is the, because the rank of this differential delta 3 is 15. This is wedge 15 delta 3. Then over here, I have wedging with the Buxbaum-Eisenbud multiplier A4. And this is just, well, the entries of, I mean, in this case, I have a cyclic module, so this is just R. Right, so this has, the entries of this have degree, well, these are the 3x3 minors or 4x4 generic matrices, these have degree 3. And this maps to R. So then what is A3? So A3 has entries of degree 15 minus 3 is 12. So what does that mean for A3 tilde? So the spinor coordinates have entries of degree 6. Right, so A3 tilde has entries of degree 6. And then I defined this map W, and the way I defined it was by lifting A3 tilde basically in the complex. So I had this map as follows, where I went from wedge even H dual to H plus H dual, and then I lifted in the original resolution to B1 dual. Okay, so since this vertical map is just constructed using the spinor coordinates, the entries of this matrix have degree 6. The entries of this matrix in the original resolution have degree 1, and then this, as such, this map W. So W has entries of degree 5. Right. So then the complex A has the graded form mat as follows. So I have 15 it's generated by 15 elements of degree 6, and then the next differential just comes from the original middle differential, so this will be in degree 7. There'll be 16 of these. And then, so the last differential, one column is the original Gorenstein ideal, so this will be cubic, so this will be R minus 10 for the column corresponding to the original Gorenstein ideal that I started out with. And then this other column coming from W has entries of degree 5, so R minus 12, like this. So in order for A to actually be acyclic, one needs to know that this ideal actually has a grade 3. So this is something I forgot to mention before, but a technical lemma that is true. So let's say lemma. So the spinor coordinates, the entire set of spinor coordinates, just depends on the starting Gorenstein ideal J, or more generally the whatever self-dual module I'm resolving. But when I take D1, I'm only taking a particular subset of them, right? I'm taking the part of the spinor coordinates that come from H dual. This because the spinor coordinates, the entire domain is wedge odd H dual, right? But I'm only taking the part that corresponds to wedge 1 H dual. So then the question is, can you, for an appropriate choice of H and H dual, actually make it so that this has grade 3? And the answer is you can, as long as the ring is, so let's say if R is local, Noetherian, and has infinite residue field, then there exists a decomposition of B2 as H plus H dual, so that the ideal of D1, which is to say the spinor coordinates restricted to just H dual, has grade 3. So it's some kind of general position argument for why this is possible. But this is an important lemma because we sort of need this to actually know that if you start with a grade 4 Gorenstein ideal, then you can exhibit it in a genuine leg 3 resolution, and the last column. Okay. So what I want to do now is the final section of this talk is basically about the question of why. And there's at least two different interpretations of this question. So one interpretation is, why is this construction useful? Like, what can it do for us? And the answer to that is it's going to help us address the goal that was mentioned at the start of the talk. And the other question is, why would one think to do these constructions, right? Like they sort of work, and it's easy to check that they work. The proofs are quite straightforward. You sort of just reduce the split exact case, you write it out explicitly, and you find that things just magically work. But the constructions seem kind of maybe bizarre and ad hoc. So why would one expect to even like write down these formulas for A and B in terms of one another, and that things should work out this way? So that's the other question of why. And the answers to both of these come from a rather deep connection to representation theory that we don't fully understand, but I'll sketch a little bit of it. So for the rest of this talk, I'll assume that R is local. So for the rest of the talk, I'll assume that R is local and has equicharacteristic 0. So I'm going to define the following T-shaped graph with 3 parameters P, Q, and R. So it's the following graph. So it has one arm of length P minus 1, one arm of length Q minus 1, and one arm of length R minus 1. Right. And associated with this graph, one can define a Kac-Moody-Lie algebra and this is finite dimensional exactly when T, P, Q, R is a Dynkin diagram, right? And in that case, you recover the sort of the usual Lie algebra associated to the Dynkin diagram. And because this is simply a Lie, still necessarily be one of the types A, D, or E. Right. So why am I bringing this up? Well, it turns out that there are various things in commutative algebra that are related to the representation theory of this seemingly completely different object. So some things that are related to the representation theory of this Kac-Moody-Lie algebra include, well, so Weyman in '89 took on the task of writing down or explicitly constructing a generic ring for resolutions of length 3, and then completed this in 2018. But the key ingredient was realizing that the generic ring that I was constructing was related to this Kac-Moody algebra in some way. In particular, for the parameters p, q, and r, this was related to the resolution with the following format. So let me see if I get this right. I might have to just a moment. So this is r minus 1. This should be r to the r minus 1. Then r to the q plus r. Maybe this should just be q plus r. This 2. Okay. And then r to the p plus q. Then r to the p minus 1. So resolutions of this form somehow or another are related to the representation theory of this Kac-Moody algebra. And I'm going to just use the word related to in a very hand-wavy way and not really explain how exactly it's related. But also, so Sam and Weyman in 21, and then later using ideas from that paper I showed in my thesis, that if we assume that TPQR is Dynkin, then, well, so I'm describing things that are related to representation theory of this guy, and I claim that the structure theory of grade p plus 1 Lichy ideals with deviation q minus 1 and type r minus 1 are related to the representation theory of this algebra. And then more recently, in unpublished notes, Weyman started looking at self-dual resolutions of length 4 and found that, so fixing p to be 2, then the following self-dual resolutions are also related to this Lie algebra. This is r to the, let's see, r minus 1, r minus, should be r minus 2, then r to the q plus r, then q minus 1, q plus 2, yeah, so r the 2 q plus 2, r q plus r, r minus 2. This is explicitly self-dual. So in particular, this middle guy is really like h plus h dual. And so explicitly self-dual resolutions of this form are also related to this Lie algebra in some way. So this may sound like completely bizarre, and like I've given you no reason to believe that these things should be related to the representation theory of this Lie algebra, but I'll give you at least one example to show you that maybe it's not so unbelievable after all. So I'm just going to go back to the Buxbaum-Eisenbud structure theorem and say it one more time, but this time using this language, and you'll see that actually it's just a special case of the above. So theorem, so let I be a grade 3 ideal, then the following are equivalent. Condition 1 is that I is Gorenstein and generated by at most n elements. Condition 2 is that I is Lichy and condition 1 holds. Condition 3 is that there exists a map F from spec R to the isotropic Grassmannian of M-planes in 2n-dimensional space, such that a particular Schubert variety specializes to I via the map F. So this Schubert variety, you don't have to if you don't know this, understand this notation, don't worry about it. It's not going to be important for the rest of the talk. But there's a particular Schubert variety that specializes to what I. So what I claim is that okay, so 1 and 2, it's clear that the equivalence of 1 and 2, right? 1 and 2 is just Watanabe's result. And what I claim is that the equivalence of 1 and 3 is none other than Buxom-Eisenbud. In the sense that if you were to write down actually what the local defining equations of this Schubert variety are, so this is some codimension 3 opposite Schubert variety inside of this homogeneous space, and if you write down the defining equations, write down the Plücker coordinates, expand them out in terms of like affine coordinates on an open cell, what you'll find is that they're none other than the submaximal Pfaffians of skew matrix. So statement 3 is really just saying that your ideal I is generated by the submaximal Pfaffians of a skew matrix. What's also interesting is that in this statement, I don't assume that n is odd. Actually, the statement is true even if n is even. It just happens that if you unpack statement 3, you'll find that the local defining equations always are just going to be generated by an odd number of elements. So, how does this relate to the earlier thing? Well, if you go back here, right, and look at this statement here, when do you get R, Rn, Rn, R? So that's the case that little r is 2, and q is n minus 2. Right, and then so is, and p is 2. So this is the diagram. So this condition corresponds to the diagram. T 2, n minus 2, 2. But if you were to draw this diagram, you would just get this diagram, and this diagram has a much familiar name. This is also called dn, the Dinkin diagram dn. And how does that relate to what's being written here? Well, the Lie algebra associated with the Dinkin diagram dn is a special orthogonal Lie algebra, so 2n. And this isotropic Grassmannian is none other than, well, if you take, it's a homogeneous space associated to, if you take the group SO2n and you mod out by the action of a maximal parabolic associated to a certain vertex, then you get exactly this homogeneous space. And if this is familiar, you should just think of this as being analogous to how the ordinary Grassmannian is, for instance, obtainable as a quotient of GLN by some maximal parabolic, right, some block upper triangular matrices. So this is just one example of how, although this, what I've written here may seem completely out of left field and very far-fetched, actually, it's, at least in this case, it recovers a familiar result. Okay. So what then is the goal here? Well, so how do we end up coming up with these constructions that are in theorem 1 and 2 from the first half of the talk? So earlier on, we had a theorem that was akin to the above, but for grade 3 perfect ideals with small type n deviation. So what we showed is that if I and R is grade 3, and the following are equivalent, which is that, so I is perfect, generated by at most 7 elements, and type is at most 2. This condition is equivalent to I is Leachy plus the above, and then this is equivalent to there existing a map from spec R to E8 mod P2, such that the preimage of a particular Schubert variety it turns out to be a Schubert variety corresponding to the word S2, S4, S3, spec R mod I. So the idea then was, well, we have this Dinkin diagram E8, which I'm thinking of as T25 or 253, I guess. So T253 is also known as E8. Right? And on the one hand, we know that this is related to the structure theory of resolutions of the form R2, R8, R7, R. But on the other hand, from this, we know that it should also somehow be related to the representation theory of, or sorry, to the structure theory of resolutions of the form R, R8, R14, R8, R, self-dual. So then the idea was, well, if these two things are both related to the same Lie algebra, maybe we can find a direct connection between them that doesn't involve going through this mysterious black box. And that's what sort of led us to start looking for constructions relating these two types of objects. So to explain how we actually arrived at the construction, let me expand a bit on this statement 3 here. Right? What is actually meant by statement 3? And for this, I'm going to probably want a new page, so I'm going to go all the way down here. So let's say I look at spec R. Oh, by the way, when am I going until? When should I stop?
I think it should be 7 in theory, isn't it?
Okay.
Yeah.
That's
So
right.
you have 12 minutes.
All right, great, thank you. So the idea here is that, so as I wrote in statement 3, it asserts the existence of some map from spec R to E8 mod P2 with some property, right? In particular, so that I have this Schubert variety X S2 S4 S3 here, and then the claim is that spec R mod I is the preimage of that Schubert variety under the map F. But what does this mean sort of more, concretely or more explicitly? So E8 mod P2, being this homogeneous space of E8, emits a Plucher embedding into the projectivization of a certain fundamental representation of E8. This is so this is just some irreducible representation of E8. It turns out to be like 147,000 something dimensional representation. It's a very big thing. But the reason for this embedding is basically because the highest weight line in here, which is to say a highest weight point in this projective space, if you act on it by E8, the stabilizer is P2. So that's how you get this embedding of E8 mod P2 into this projective space. And so what does that amount to more concretely? Then this is the data of some matrix, a row matrix, a map from L omega to dual, this representation of E8, to R. And then inside here, so I can think of this map here as being described by some row matrix of this form. And then inside of here, the coordinates here are the Plucher coordinates, the projective coordinates in here. And I know that this Schubert variety is defined by the vanishing of some Plucher coordinates. So let's just say these Plucher coordinates here, some Plucher coordinates defining the Schubert variety X, S3, S4, S2. Okay. So okay, let me attempt to color code this a little bit. So I'm not going to fully explain the color coding, but it will hopefully help me contrast things a little. So I'm going to write this as more. Okay, so. Alright, so there is some subset of the Plucher coordinates of this R point of E8 mod P2, and the claim of this whole picture is really that your ideal generators are here. Right, that's really what this picture is saying. Right, these are the Plucher coordinates defining this Schubert variety, and by this map F, they specialize to your ideal I. But it turns out that there are some other embeddings of E8 mod P2 that you could also look at. So, for instance, you could also embed this homogeneous space into a Grassmannian of 8 planes inside the representation L omega 1. Some other representation of E8. What it exactly is not really important, but there is such an embedding because it turns out that there is an 8-dimensional subspace of this representation that if you act by E8, this subspace is stabilized by P2. So that's how you get this embedding into this Grassmannian. And likewise, there's also an embedding into the Grassmannian of 8 planes in this yet another representation of E8, this L omega 8, which happens to be the adjoint representation of E8. But that's not important for what I'm about to say. So, concretely, what is the data of these maps? Well, I can express them as matrices as well. So I have a map from this to R8 from L. So map from L omega 8 dual, and I also have one from L omega 1 dual to R8. And the beautiful fact is, well, what was I saying earlier? I was saying that the ideal generators show up here, Or if I think about the resolution of the ideal, I can say that the differential d1, in other words, shows up here for the ideal of grade 3, this grade 3 perfect ideal I'm looking at. And the beautiful fact is that if you look at the embeddings of E8 mod P2 into these other Grassmannians, and you write down these representations as like matrices, you can actually see the other two differentials of the resolution of length 3 in these as some matrices of these other two matrices. So in particular, inside this one, you'll find, if you identify things correctly, you'll find D2 dual, and then in this one, if you identify things correctly, you'll find D3. Right, so this R8 is really, this one is really A2 dual, this one is A2, and then here I have, for instance, A3, A1 dual, and this is A1. If you identify things in a certain way, you'll find this. But how does this relate to the earlier discussion of theorems 1 and 2? Well, so what did theorem 1 say? Theorem 1 said that if you look at a column of D3, right, a column of this guy here, then assuming it has grade at least 4, then it actually has grade exactly 4 and is a Gorenstein ideal. And the substance of theorem 2 is that you can always, if you start with a Gorenstein ideal of grade 4, you can exhibit it as such a column like this. And that's the important thing. So what is this column? Well, let's go back to this picture. Now I'm going to move everything down a bit. So here I have a R point of E8 mod P2, but I can lift it to a point of E8. I mean, because R is a local ring, so I have no problems doing this. For instance, spec R, this R point of E8 mod P2 lands in some open Schubert cell, and I can lift any open Schubert cell non-canonically to the group itself. And what that amounts to doing in terms of this matrix is I'm saying, well, this matrix here, this 8 by, well, there's a lot of rows. This 8 by something matrix is really the first part of a square matrix. And this whole square matrix is represented by the action of this R point of E8, whatever I lift this to, right? Acting on this representation L omega 1 dual. And then, what I want to do now is I'm going to look at the first column. The first column of this matrix, right? So this is some L omega 1 dual. And then I have my grade 4 Gorenstein ideal showing up here, and if one looks at the Plucher coordinates, the coordinates on this representation that correspond to the entries in which my grade 4 Gorenstein ideal are appearing, these turn out to be none other than the Plucher coordinates cutting out, defining a different Schubert variety in a different homogeneous space. Right, so I can think of this whole first column of the square matrix as defining an R point of E8 mod P1. And the 1 here comes from the fact that it's this fundamental representation associated to omega 1. So what I'm saying is that this picture right here, this map right here is the data of this matrix. And then if I restrict myself to looking at this sum matrix here, these are the Plucher coordinates defining a certain Schubert variety. It turns out to be X, S1, S3, S4, S2. Then this Schubert variety, S3, S4, S2, specializes to the Gorenstein ideal J, where J is generated by the entries of this column here. So, furthermore, it turns out that, okay, well, you see the last differential of the length 4 resolution here, but just as how you could see the other differentials of the length 3 resolution in these other embeddings, it turns out you can also see the middle differentials of this length 4 resolution. They show up here. So there's, maybe I should not make them perfectly overlap, but there is a certain way that you could unpack things to see that the middle differential delta 2 for res of R mod J appears here. And what you see, right, is if you believe this picture, then this picture, if you take it at face value, tells you that this middle differential of the length 4 resolution should be comprised, in part, it should be comprised of this D2 dual of the original guy. But the other part comes from something else. So the question is, what is this something else? And from the theory of higher structure maps as developed by Weyman, it turns out that this next block in this matrix can be interpreted as multiplicative structure for the length 3 resolution A. So what I'm trying to explain here is that although when I presented the constructions of the first half of the talk, they might have seemed sort of arbitrary and ad hoc, if you set things up and you sort of follow what representation theory predicts, the constructions almost write themselves. Like they sort of tell you exactly how you should disassemble and reassemble the data from A to get a complex B. Okay, but I'll just end by stating the theorem. I've basically sketched a proof of it now. So the theorem is that if I and R is a regular local ring, is grade 4, then the following are equivalent. Condition 1 is that I is grade 4 Gorenstein. 2 is that I is Lichy, and 1 holds. And 3 is that there exists F from spec R to E8 mod P1, such that the preimage of this particular Schubert variety, S1, S3, S4, S2, is spec of R mod I. Or maybe I should, okay, I think I was using J for the, let me just be consistent with my notations. J.
What do you assume in 1 in addition to grade 4 chords?
Generated by up to 8 elements. Yeah, thank you. Generated by at most 8 elements. Right, I wish we had a theorem for all grade 4 Gorenstein.
Yeah,
we do not have that.
You need an assumption there.
Yeah. Okay. So the bulk of the proof has basically already been, the pieces of it have already been presented in the earlier pages. But maybe the one thing that I should just remind you of, like why, for instance, is this regular local ring assumption there, and also it's helpful to have this equivalence of 2 and 3. This is already established in my thesis, but the fact that this equivalence with the Lichy condition allows us to reduce the case that R is complete, because this follows from the theory of universal linkage by Hünnecke and Ulrich. So I can, without loss of generality, assume that R is complete, and then if R is a complete regular local ring, then I can use the result of Custon and Miller that says that the resolution of J actually has this explicitly self-dual form, which is necessary for the construction for it to produce this resolution A. So that's sort of the reason why there's this regular local ring assumption here. But the rest of the argument is basically presented here. The idea is that once you know that there is a resolution of length 3 that exhibits your Gorenstein ideal and its less differential, then you sort of just chase around a bunch of representation theory, and then you just magically find by this diagram that by taking this original map from the length 3 guy and then lifting it and then looking at it in a different homogeneous space, you just magically get the map that you want for the grade 4 Gorenstein guy. Okay, so I think I'll stop there and take questions.
So in particular, the question is, the grade 3 you have is Lichy, the one you build.
Yes, so in both of these theorems, so if I start with this grade 4 Gorenstein guy generated by at most 8 elements, then the construction of the resolution A will give me a guy in this setting. Whoops. In this setting. So in particular, it will be Lichy. Yeah.
Okay. And then you can use that theorem and vice versa. Okay. Yeah. And in general, you always have that the guy that you build is Lichy if and only if the grade 3 is Lichy if and only if the grade 4 is Lichy, no?
Right, yeah. So this is a work in progress thing, which we basically have like the outline for a proof where it's just that there are a lot of small technical details that have to be ironed out. But indeed, that would be a generalization of the statement, right? So the statement that if I is Lichy, then J is I is Lichy if and only if J is Lichy would immediately imply this theorem. Provided that you assume the equivalence of 2 and 3, which already follows from my thesis. Because once you know that, then, well, this I is Lichy, if also J is Lichy, which gives you 2, but then 2 just implies 3. So
yes.
Yeah, so that is a stronger statement, the statement that I Lichy, if and only if J Lichy.
But you do have an example of a case in which it's not Licci in the two columns, there are two Gorenstein ideas of grade 4 but are not linked together, no?
Right. Yeah. So that was
a linkage class.
Yeah. So great. Yeah. So I didn't get to talk about that, but that was sort of the purpose of. If I had time, that would have been the purpose of this example. Where did it go? Oh, this one here. Right. So in this example, I produced this resolution of length 3. Where in the last differential here, this D3, one column, the column corresponding to this guy, was the original Gorenstein ideal of grade 4. So this column was just the 3x3 minors of a 4x4 matrix, for instance. Sorry, that's right. 3x3 minors of a 4x4 matrix. Right. And then this other column is some other potentially Gorenstein, if it has grade 4, then it's also a grade 4 Gorenstein ideal by theorem A. And by computer calculation, I've checked that it can be made to have grade 4. And actually, by numerical criterion of Hünneke and Ulrich, you can show that this ideal, the ideal coming from this column and the ideal coming from this column, cannot be in the same linkage class. So this is a weird thing, right? Which is that if one of the two is Licci, then the other one must be Licci by this work-in-progress result that says that, okay, if one of them is Licci, then this ideal is Licci. Then this ideal being Licci means the other one must also be Licci. However, if either of them is not Licci, then the other one might not even be in the same linkage class.
Yeah.
So there's a question there about what kind of maybe equivalence relation is generated by this and how that compares to linkage.
Are there any other questions, guys, besides mine? Okay, so you don't have any other question. Xianglong, thank you so much. Thank you very, very much.
Thank you for having me.
Thank you very much for the interesting results. Thank you.